Hassan to introduce himself and there.
Okay. Good. Thank you very much. Hello, everybody, and thanks for coming to this seminar. It's a pleasure for me, and thanks, Amir, for the invitation. I'm, as you can see, my name here, Hassan Al-Midifirzi. My background is more mathematical finance. I'm working for Royal Bank of Canada, RBC, since 2016, the beginning of 2016. I work in 2 different departments, model validation, and since a couple of months ago, I joined the wholesale credit risk in the model development side. Regarding the machine learning and AI, I've been interested in this field since when I was doing my part of it. I was interested when I was in France. I was doing a 1-year postdoc at University of Paris 1. And I have seen different people in the Department of Management at the University of Paris 1 and ESCP Europe Business School. They were talking about more application of this model in economy and econometric fields. So the starting point started over there, and then when I joined RBC, I started talking with some people that they had like hands-on experience with machine learning and the application on it, especially in different industries. Understanding the language, the jargon, it was a bit difficult for me at the beginning, but then I get used to it and I understood it better and better. I started reading some books, meeting different peoples, and fortunately we have seen the financial institutions, especially the banks that I'm aware of, they try to focus and dedicate some personnel working on this type of models, at least for the sake of understanding the models better and hopefully finding an application, especially in the domain that I'm working on in risk management and in model validation. Let's say if in one department in the banking or insurance companies, we receive, like imagine for a second you're a model validator. You receive one of these models, machine learning models and AI models. I'm talking about those that we call them like black box model. We're not completely or 100% aware of what's going on inside that engine or the model. So as a model validators, the people, they have to be aware to understand, attack these models, how they can attack, understanding the model from the input to the output, understanding the connection between these two, perform some analysis, including sensitivity analysis for these models. And so that was a starting point kind of for me to go over machine learning models, especially neural networks that I was interested in, because that was not my field of study, but I thought that, okay, I have quantitative background, skills, tools, and I just want to focus on neural networks and understanding from the input layer all the way to the output layer, try to understand how it works. There are some like hyperparameters over there, if I put in that jargon, how you can set them, what's the impact of these hyperparameters when you start working with one of these models, what's the role of input, the hidden layers in between. Because at the beginning, when I was talking with people, they were referring to some of these models. They had a perfect 99.9% of like predictive power, and the performance of these models is amazing in the classification, or image recognitions, handwritten recognition. So I delved into these models and this application. It was quite surprising and interesting for me, because I used to work with traditional statistical models like GLM's models, including and then time series models, that you can find it quite often, the application of these models in the banking industry, in the credit side as well. So for me, it was a big interesting to see the high performance of these models. But at the same time, I wanted to see the application of this in the industry that I am working on, working in this industry, and the question that I'm working on in my daily work, in my daily job. And so we try to see and investigate as much as we can in the application of these models in financial industries. So I came across this article, this paper on Archive. Its title says Explainable Neural Networks. So we call it XNN, based on additive index models, and they call them AIMS for facility. So so I came across this paper like last month. Basically, they submitted this model in Archive on June 5th, 2018. And this paper basically is submitted by a model risk team from Wells Fargo Bank in the US. Based on my discussion with some of my colleagues that they have connection with the banks and this team specifically, they told they have a strong team. They're working there, researcher working on AI and machine learning and their application in finance. And so I came across this paper. To me was, and still is, interesting the way that they attack the problem of being black box model and how they try to understand the model and how they can use the proposed approach as a surrogate model to approximate the main model. Let's say feed forward neural network, you feed it to your problem, you get the amazing performance, and then you can basically use this XNN model to somehow approximate and understand the main model for the sake of performing some analysis, getting the connection, the relationship between the input and output of the main model. So with this introduction, I'm going to move forward and start providing some motivation here. In the first slide here, you can see. So a couple of days ago, I came across some biography and from Geoff Hinton from U of T and Toronto Life magazine. It was basically the interview was from January 2018, if I remember correctly. So that paragraph, it was interesting for me. So I tried to put it here for the sake of make a connection also with the title of this presentation and the purpose of this presentation today. So as we know, and based on the biography I've seen from Geoff Hinton, he got some difficulties when he was doing his PhD because his PhD supervisor didn't believe in what he was doing. Back then he said, this is maybe it's useless, or you cannot come up with a good results. Forget about this, let's focus on another problem for the sake of finishing your PhD. So, and he was saying, Geoff Hinton, he was saying that I was more curious and I believed in intuition more than just logic. So, and the way that brain works, I was kind of confident that it's gonna result in something interesting. But having said that, so he also, at the same time, he's curious about what he's working on, the world that he's dealing with, and the type of modeling choices that you select to address your problem. So meaning that being a black box, giving you a perfect performance is good, but is not enough. Why you come up with this performance, that's also important. And the second one, I just wanted to provide you, this is one of the famous quotes between statisticians, specifically because of the George Box, was a pioneering back then in statistics. He said essentially all models are wrong, but some are useful. The first glance, once you look at it, is a bit, meaning most of the models that we're working them are wrong. But the way that I look at it is, I look at it in two ways. To me, it has a connection, this code, between predictive performance of a model and the level of complexity of that model. If you have a complicated environment like the question, the world, and you try to address it with the simplest model, just the linear model, then you fail because the performance of the model is not as good as, or is not the way that you expected. So we can put that in that context, that these models, we look at the performance, they are wrong. But if you look at the second part, some are useful. To me, this means this second part is talking about, okay, if you try to fit a complicated model to address and to model the underlying problem, the real problem, then at the same time it's going to be so complicated you cannot understand it. To some extent you can approximate that with another model which is useful, which is not completely like the first part. The performance is not very well, but it try to approximate the main model with relatively good approximation. Meaning that you can approximate the main model with another secondary model that is easy to interpret, is easy to find the connection between the input and output, what's going on. If you are trying to understand what was the main reason for this output, how you can answer that question. One of the important questions, at least I can put it in the banking industry context, is you can apply neural networks for the sake of, for example, credit scoring of a client. And for a second, assume that Hassan, I am a client for Bank X. I go and I ask for a line of credit, and then based on the information that I provide and what the Bank X has, they are trying to feed the information to the model they already have, black box, for example. And the rating or the credit score for Hassan is going to be so low, for example. It's not expected at all this is going to be my credit. So I check into the branch and I ask why my credit score is low. I didn't have any mispayment. I paid all my loans so far very well and on time, without any delay so can you justify why I came across, why this is my credit score is low? What is the main factor for that? If they apply neural networks with, let's say, 10 hidden layers, each layer is 100 nodes, what's going on? What was the main motivation? Can you tell me, like, maybe because Hassan living in the neighborhood X, and the neighborhood X is treated as a risky neighborhood, so we are not going to issue a loan to Hassan. The same problem applies in insurance companies as well, especially insurance companies when they are trying to give you a code based on, for example, zip code. As I'm a resident here in this city, for example. I'm just providing an example. Like, I'm living in downtown, so I mean, in that neighborhood, because it's so crowded and there is a risk of like accident, highly, the rate of accident is high, then probably the insurance company gives me like a higher premium. But this is fair just forget about the math, like the math and modeling behind it. How you can justify that? So before going into the technical part of the presentation, I'm just referring to a book. Probably you have heard about this book. It's called the Weapon of Math Destruction by O'Neill, if I'm not mistaken. But Cathy O'Neill was of the mathematician in the U.S. and so she moved to Wall Street and she worked there for a while, working in data science, and then she quit. She wrote this book. I didn't get a chance to read the book as a whole, but she has one famous code, and she's trying to provide the reasoning why misusing this black box or the advanced algorithm is dangerous. The way that she is providing an example, maybe she's over-exaggerated, but somehow we can get the point. She's saying that if you are using these models the way they are, like you don't select a good feature, if your feature engineering is weak, then this result in the poor people getting poorer and the rich people getting richer. That's the whole message. And then the example is zip code, for example, for the insurance company, or if a poor guy like is gonna go and apply for a loan, then they reject it. That person cannot check into the university, getting higher education, find a better job. So that's the way that, you know, in this book is also talking about. To me, is important to address this from the beginning, the input of this model to the output, feature engineering to what's going on inside the model and the output. So putting all these together, I think it's enough for the introduction of and the motivation of this paper. So here in this slide, I just wanted to highlight some questions. When I started working and understanding these black box models, like neural networks, the people they were referring to this model, they are black box. It's difficult to interpret these models, to understand them. So I was asking myself these questions. Why interpretability or explainability of these models are important? If I have a model that gives me the perfect performance, who cares like what's going on inside that box? I don't care. Or another question, at what cost we can come up with a model which is highly explainable, at the same time we have a good performance of that model. Keep the balance between these two, model complexity versus the fidelity and of that model as well. So this type of question I was trying to address it in introduction. I provided some examples, but I just wanted to make a connection with the approach that the article that today we are going to go over it with the current approaches for understanding this black box model. There are I just listed a bit of these the current approaches that you can find in the literature. One of the famous is called additive feature attribution methods. Two of the famous model that trying to interpret this type of models are local interpretable model agnostic explanation, which you can call it LIM or LIME. And the second one is layer-wise relevance propagation, LRP. I think that the first one or the second one, we have someone is going to go over it and present it maybe in August, around that time. So these two papers are interesting papers. And then the way that they try to attack the problem of being black box and understanding these models is mostly is a local approach. What does it mean with local approach? Because we have global approach and local approach. The way that local approach here for these two approaches work is as follows. They don't try to manipulate or play around with the main model. They say, okay, I have a neural networks with a given architecture. The performance of it is very well, so I'm okay with that. But I am trying to approximate for a given input. That's why the locality, the local comes from here, local interpretation. For a given input, they are trying to solve an optimization problem to come up with another approximation for the output of the main model, which means the output of the black box applied on the given input. So we are given input x1. From the main model, we get output f of x1, which is a black box f. We don't know what's going on inside of it. But we're trying to approximate f of x, which already we know it, based on another function, which gives us a good approximation in some sense. The sense, the distance, the whole architecture of that optimization problem are discussed in this paper. You can see also at the end in the reference, you can see the full name of the paper as well. Another one is LRP. LRP approach is again, you can verify it, and you can see that this is also a local approach, meaning that, so instead of approximating the output, they are trying to get the output f of x1 and try to somehow propagate the f of x to the backward to the input layer. They are going to see the contribution of each node in each layer in the final output that we got. Somehow they are going to see, how relevant this node for this f of x, how relevant is this layer, for example, is for the given output. So these two approaches are local approaches, meaning that for a given x, it's not global. You cannot draw a firm conclusion about the whole of the set or the space of your input. Yep.
Can I ask a question?
Of course. Yeah.
Sure. What's the issue with LRP? Because when we're in the image domain, I know that we are talking about the numerical domain, but in the image domain, we have the same thing that they call it saliency map.
Yes.
And with the saliency map, at the end of the day, you are getting the value of each pixel at your output,
yes.
how that pixel is relevant to the input.
Yes.
So I wonder that on that domain, we're getting a very good understanding that that black box is working. I'm not following it. What's the issue with LRP that we have to go for the global?
Okay. Yeah. Interesting question. Yeah. So for image recognition, yes, absolutely, because we are for a given picture, we don't care about this second picture, right? We are given one picture, is a Hassan picture, and then you're going to understand if this is Hassan, the true picture of Hassan, or no. We are not going to compare that with Amir picture, because it's important for us to understand. But in the domain of for example, in finance, that we are working in, is important to come up with a global conclusion about the global relationship between the input and the output. I provided like the credit score for that in our example. It's really important for a model in this field to understand what's the real connection between the given input or the given feature and the final output as a whole. What we can say, if I tweak the given feature, and what is the impact of that change in the final output as a whole. Because here we are not talking about, for example, a specific case. Here we are talking about we are going to get the firm and the global conclusion about this type of models and behavior. About the image recognition, yes, absolutely. And I think the whole idea of LRP comes from the image recognition and the performance overall, the understanding, and being a local is pretty much address the whole problem. But in other domains, it's important for the sake of sensitivity analysis of the model. We perform sensitivity analysis on a statistical model or regression, for example. We understand if we tweak the one independent variable, then then we can try to address, to do the sensitivity analysis and see the impact of the given independent variable and the role of that coefficient of that independent variable. So we can mimic that and try to apply and ask ourselves the question how we can perform that analysis on a black box model.
So when you say f of x,
Yes.
is it just one variable like x1? When you say local, you're talking about one specific variable, or you're talking about the entire
Entire space,
list?
you mean?
Yeah.
Are you talking about the entire space or entire input layer?
Input
Yeah,
layer.
yeah, entire input layer.
Okay.
For example,
For
for a vector.
Right.
If
For
I put
LRP.
it,
For
for,
LRP.
yeah, or for the first approach line.
Okay.
Yeah. So we are given a vector of inputs.
Yes.
Let's say we have 5 features, 5 nodes in the first in the first layer, input layer. So as an example, we have x star. X star is x1 star, x2 star is a vector in 5 dimensions. So I'm talking about that one as a vector. So you
Sorry,
can,
before you move on, I didn't understand your question though. Are you asking why it is important to have a global explanation, or?
To be honest, when we are in the image domain, with the saliency map, you're calculating the effect of each pixel in the output from the input, the way that LRP is working. So basically, you're calculating that if I'm going to, for example, turn off 1 pixel in the output,
Yeah.
how my input going to change?
Right.
And then you found that, okay, for example, which part of the inputs has the effect in my output.
Sure.
So that's the concept of the saliency map. I never saw that they are using the LRPs in the numerical domain. That's why I'm asking. Maybe it's possible, maybe that. That's my question. At first I thought that, okay, each pixel could be represented as one of those elements of our whole picture, but apparently that's not the case.
So over there, you can still apply LRP or local methods in numerical cases, in other questions in different industries. But the problem is, applying case by case is not enough. A specific case. I'm doing this for X star, and I'm doing this for Y star. Then what? Like what's a firm conclusion you can get about the specific feature in the first layer? That's important. In some domain, this is important to understand that the connection between the input and the output, and draw a firm conclusion globally, not locally.
So when you say locally, you mean for specific outputs, you find out, LRP finds out which input values are, which input features are important.
And then the hidden layers as well.
Yes.
All the way back. Yeah.
But for only for certain.
For
outputs.
a given example.
Gotcha.
That's why we call it.
Given input, not output.
Yeah, given input.
Right.
Because we are given one input, and then we perform the black box on the X, let's say X star. Then we get f of X star.
Yeah.
Then we are trying to see the impact
Yeah.
or the contribution of the hidden layers, because that's important for us to understand the contribution of the hidden layer and node in a given hidden layer.
Yes, still no question. What's the local and the global? What's the difference between local and global?
So global meaning that you can get a complete and a conclusion about the relationship between, for example, I just make it simple, between the input and the output.
So like the linear regression, you basically understand it globally, right?
Exactly.
Okay, what's the local one?
So the local approach that here, for example, LRP, is like the example that our friend provided with image recognition. It's case by case. For a given picture, then you can back propagate, and then you can see the contribution of the inside, what's going on with the hidden layers inside of the black box. You cannot say something globally. Y equals to alpha plus beta x, just a simple linear regression.
Yeah, I understand the difference between the image and the like a regular linear regression, because image you don't have fixed features, right? The feature
The input, yeah.
But linear regression, the feature is defined.
Mm-hmm.
So
I don't know about this one, but in case of the image, we just exchange 1 pixel of the output and then calculate that what's the effect of changing that pixel in the input.
Kind of sensitivity.
So
knowledge.
then, yeah, and then we are doing these things for all of the pixels, and then we'll be coming up with the new map that they call saliency map, and you can make that pictures from whatever layers that you want it. You can, because it's basically you are calculating your errors backward from the input to the from the output to the input.
Yeah.
So backward the
Yeah.
neural network, get back to
Get back. So you can make it from the, whatever layer that you want. But apparently here they are using the different approach. So
No. So LRP and so I mean, each of these methods is gonna take like one session. I think down the road in August, one of our friends is gonna present in details what does it mean this approach, lean. But just here, for the sake of comparison, with the main paper that here we are going to talk about, is that these models, basically these approaches, they are local in the sense that we described. They're based on like a given input. And another difference between that and the paper that we are going, the XNN, Explainable Neural Network. Explainable Neural Network itself is a model and is trying to build a neural network that somehow the author of the paper, they claim that there is a built-in interpretability property of this model in this X neural network. And then down the road we are going to explain what does that mean. Does this architecture fully 100% address the problem of interpretability, building characteristic of this model? Do we see the 100% the relation between input and the output from this XNN or no? So that was the purpose, I think, I was thinking about to present it today in this session. So if we move to the next slide, here I just wanted to briefly provide some motivation based on what I see in the paper and what I was thinking afterward, the way of like reverse engineering, and also how the idea of this architecture came into their mind. If I want to replicate that in my mind, what was the steps that to come across this type of architecture? So apparently, based on the submitted article, they are using a class of models. It's called additive index models. We call it AIM. So these models, they have this position number 1. So they can be written as a linear combination of a nonlinear function. So if you look at it in equation number 1, excuse me, Amir, can I use a pointer or?
There is a laser, but it wouldn't really work on this.
Okay, no worries.
Okay. Point.
Yeah, okay, by finger. Cut my fingers off. So in equation 1, just to the sake of simplicity, so what we have k different functions. Look at G1, G2, and Gk. Each of these Gi's, for example, let's focus on G1. G1, the G1 applies on a specific form of its domain. It's a linear combination of the input, which somehow resemble the linear regression, for example. If you look at the linear regression, alpha 0 plus beta x. So the idea comes from, I think, over there, inside parentheses, you have beta b1, beta 1 times x in the vector form. And then on top of it, you apply another function, g1, which g1 can be linear or nonlinear, which I think the purpose here is not being nonlinear. So if you look at equation 1, if I put it just in a simple form, is a summation of k nonlinear function applied on a linear combination of inputs. So why this class of functions are important, and how we can make a connection between the architecture that we are going to present and this equation. So this equation, basically, this class of models has been shown in a paper back then, like I think more than 30 years ago. So these functions are, in a technical term, they are dense in a space of like multivariate function. What does it mean? It means that, let's say you have a function f, which takes n inputs, x1 all the way xn. And then it gives you a real number. So you can show that for a given f, and for a given error, in a technical term epsilon, you can approximate the given function f by one of the functions here, if I call it g, for example, or h. So f can be approximated, because for the sake of, I don't want to make confusion here. So because here the representation is f is a linear, so f itself is one of Ames model. Let's say we are given h. I provided you, I give you the example. H of the vector x. H of x for a given error, and we can find a function f, an arbitrary or maybe large k, that the difference between fx and hx, the given function, is smaller than epsilon in a term, like absolute term, for example, in a given norm. So if I put it in non-technical way, so for a given function h, and for a given error, tolerance, for example, we can find a number k that one of the Ames model function can approximate the main function h that is given to me, based on that tolerance.
Okay.
So this is a whole. So meaning that you can approximate very well any function by one of these functions. That's a way of like being dense in the space of multivariate function. So the idea of the x and n comes from here. So the authors, they're trying to tweak the Ames model in the previous equation by some minor changes, not a big difference between the equation 1 and equation 2. The difference is just here. You can treat gamma 1, h1 as g1 in the previous equation.
Yeah.
That's just a linear combination. Why they trying to use this form? We're going to see later on in the architecture. These little gamma 1, gamma 2, the coefficient of h functions are basically your weights in the final, connecting the final hidden layer, or to the final layer. They are somehow the weights. So they have some terms that we are going to address them here. The first hidden layer in XNN, explainable neural networks, they call it projection layer. So we have input layer, we have first hidden layer, which call projection layer. And then in between we have some subnetworks. And the final one, which is one node, is called combination layer. So I think it's better to provide an example here. What does it mean? So for the sake of understanding here, I provide the fully connected feed-forward neural networks on the left-hand side and the XNN model architecture on the right-hand side in this slide. So just for a second, look at left-hand side, the fully connected here. We have two hidden layers, and the input layer and output layer, which is one node. If you look at it, every single node in the input layer is connected to the all inputs in the all nodes in the first hidden layer to the second hidden layer, and so on and so forth. So it's fully connected. But look at the architecture of the XNN model here. If you look at the first layer, which is input layer, which is fine, no changes. The second layer, as you can see, so there is a full connection between the input layer and the first hidden layer, which is called, they call it in their term, is called combination layer, projection layer. And so far there is not a difference between fully connected feed-forward neural network and XNN neural network. The story starts here from first hidden layer onwards. From first hidden layer, so first of all, what kind of activation function they apply in the first hidden layer? The activation function they use is linear activation function. It's not sigmoid, it's not ReLU, it's just a simple linear activation function. We discussed it why. So for a second, assume that the output of the first hidden of each node in the first hidden layer is in the form of beta 1 x. Do you remember beta I x? It was inside the parentheses in the equation. So the output of each of the nodes in the first hidden layer, they are used as an input for each of these boxes here you can see. What are these boxes? These boxes, for example, here, for the sake of like illustration, here we have 3 boxes, meaning, so each of these boxes represent one of those function, h. If you remember in previous slide, we had here h1, we had h2, hk. And if you remember, the output of the first hidden layer was inside parentheses.
Yeah.
The reason so maybe you guessed it, why they use a linear activation in the first hidden layer. Because they wanted to get inside parentheses. So they are, based on this presentation, they are trying to build up the architecture of the neural network. So they already built the beta k times x, the output of the first hidden layer, the projection layer. And then, so the second step is trying to, they have to come up with the architecture for each of these h1, h2, and hk. How the way that the architecture that they are providing to train and to get the shape of each of these functions, h1 all the way to hk, is like this. Each of these boxes itself is a feed-forward, fully connected neural network. So inside each box itself is a network. Again, fully connected. How many layers? So we don't know. Again, how many hidden layers? How many nodes in each layer? What are the hyperparameters? The same question that we had for the standard fully connected neural networks on the left-hand side. We have it here in each of these boxes. So we are going over all these the issue that we just discussed about. So for a second, let's assume we get the output of each box, which is a number. We call it h1 because it's a function. So we don't know what's going on inside the box, but it's applied on the beta 1x because it takes it as an input. So that's why we call it h1 of beta x. So on and so forth. So the final task is, if you look at the previous equation, so somehow the authors in the paper, they build hk, they build inside the parentheses beta k times x. What's left? The gamma. So that mu, you can tune it, is a constant. But the betas here, the way that they come up with this architecture, the betas are just basically, if you look at it, if you apply, again, a linear activation function on the final node. If you apply the linear, then you expect the weights on each of these, the connecting between each of these, the output of each of these boxes to the final node should be gammas, the little gammas. So if you look at equation 2, basically this architecture on the right-hand side in this slide, try to build the equation 2, based on equation 2. Any question? Yeah?
Yes. So so I understand how the right thing
works,
corresponds to the equation.
Exactly.
But So two questions. One is it trained by backpropagation?
Okay.
It shouldn't be too difficult to answer because that's just summation of bunch of
Exactly.
neural nets. So,
Yes. Yes.
But the second thing is that it looks like you grabbed a simple neural net, like a fully connected multi-layer, neural net, and replaced it with a bunch of those things. So is there a relationship between the capacity of this one and the capacity of each of those, right? Because what if, in order to achieve that, you need to have a very, very complex, model on the right rather
Yes.
than
Just
see what I mean?
feed-forward neural network. Yeah. Are you talking about why somehow? What's the benefit of this?
No, benefit, I guess you're going to tell us because there is addition, it is
Yeah.
easier to interpret, etc.
Yeah.
But I'm asking in terms of, like, say, computational resources, right?
Yeah.
There's the complexity of the left model,
Exactly.
and the capacity of the left model, and the capacity of
Of the
each
right
of the
side, yeah.
ones on the right.
Yeah.
Because the additions are easy to
Exactly, yeah.
in terms of computation.
Yeah.
The cost is coming from computing H's.
H's, some
Right.
networks, exactly.
Exactly. So now my question is there a relationship between the capacity of what you have on the left and the sub-networks on the right?
I think, yeah, that's a pretty good question. Yeah, absolutely. So first of all, each of these boxes, as you mentioned, so is pretty much a feed-forward neural network. Is what in the left-hand side. So to me, one of the problem still with this architecture we have is a computational problem for this XNN. If you tell me, for example, a fully connected feed-forward neural networks, if you come up with many layers, if you have a problem in terms of computations, in terms of all those problems, if you go with a stochastic gradient descent optimization approach to come up with the weights, the same problem still we have it here for each subnetworks. So if you have a problem here in terms of computation, here you have it. But in the paper, what the author they submitted, they talk about the architecture of each of these HIs. So based on the evidence they provided, they claim that for pretty good class of models, still they don't mention which class of model, but for a good class, they go with just two hidden layers. Two hidden layers, and if I put it here, we go back to the previous slide, but just for the sake of illustration here, they use two hidden layer. Each layer has 25 and 10. First hidden layer 25, second one 10 neuron, and the second case 12 and 6. They tried on two different architecture for the subnetworks. So you can ask the question, if I go with,
So hold on, that's good. So that's
Yeah.
the number I'm looking for.
Yeah.
But that's an approximate to what? Like what is the other? Like what is the left side? In your.
no, they're not going to approximate the left side. So I think your question is,
So what I want to know is that what is the size? You're telling me the size
Yeah.
of the one on the
Yeah.
right, right?
Yeah,
So
yeah,
that's
absolutely.
Great. That's
Yeah.
great. But
Well,
is
what's the size of
corresponding
the left-hand
one,
side?
right?
So exactly. So what is inside in this article? They are not going to. They don't assume a given architecture in advance. What they are interested for the moment, I'm assuming that they are going to submit a second or third version of the paper. But for the moment, they are trying to kind of come up with an architecture that approximate fx. So fx, let's say fx, x is a bivariate, e to the power x1 times sine of x2. So you can do simulation, you can generate 50K of numbers. So from x1 and x2, and then from your function f. So f has a nonlinear representation, e to the power x1 times sine of x2. They are trying to train architecture like this, x and n, to somehow approximate the underlying model, e to the power x1 times sine of x2. Here we don't have a fully connected neural networks as an underlying model. But what they claim, and I think that was a purpose, one of the motivation for this article is to somehow they come up with a good approximation for the main model, which is the left-hand side. They don't explain anything in the paper if this model is a neural network, the underlying model, or is not. So they are trying to just apply it, the first step, for a given function. They are trying to build a connection, an architecture, to somehow approximate the main model. Yes?
Did they mention anything about k, the value of k? How many?
Yeah, is it test cases? They provided 3 examples in the paper, and for each of these examples, they tell you how many k's they assume.
Like how to come up with the k value?
That's another question.
Yes.
Exactly.
It's an input parameter, right?
Yeah, absolutely.
You have
Hyperparameters.
to optimize over it.
Yeah, how many k? You can use it with cross-validation. You can, the techniques that you can. Thank you. Yeah, pretty good.
Does the clicker work?
Yes, thanks.
So the number of the k is not related to architectures.
It's not. Sorry.
So then the number of the k
Yes.
is not related to whatever architecture that I have on the left side.
So.
Or the function that I'm trying to approximate it. We don't know it.
We don't know it.
Okay.
We don't know it. Yeah.
So one observation is those sub neural networks that each of those H1
Yes.
is related to, they only have one input and one output. It's a 1D to 1D, right?
Exactly.
So in a way, it's kind of like some of the complexity is kind of folded into the beta matrix.
In each box?
But each one of those are single because you're only approximating 1D to 1D.
1D to
So that's why they
Which
use
is
only
very
2 layers.
simple, right?
Yeah,
Which is very
yeah.
simple to.
Exactly.
Yeah.
Exactly.
What
But,
do you
but
mean? You mean the for the beta X there is just one feature?
One number.
yeah, just one number.
Yeah, the input
Is
for
this
each
one
of
number?
those sub-networks is
Yes.
one dimensional.
It's one dimensional.
Because after you did the dot product, the beta times x, it becomes one number.
You use one number to propagate to a hoop, build another.
Yeah.
So
Yes,
you-
absolutely.
you have to-
Exactly.
approximate
Sounds
down here.
weird, right?
Yeah, but it
But-
That doesn't make sense.
Yeah.
It does. You can use
You do
numeric to
one number,
approximate,
you propagate through, I mean 100 hidden layer, hidden
Yes.
layers.
Yeah.
But they won't give you anything. I mean, just you.
Yeah.
I don't think
That's why I
you-
don't have 2 layers. That could be.
So
I think it should be it's a vector. It should be a vector. I don't think it's a.
No, it's just a single
It's a
number.
single number.
Yeah, it's just a single number. So, yeah, but again, this is a supporting evidence. So, what is inside parentheses is beta kx. Is it a number? Beta k is a vector, x is a
It's a
vector.
vector.
Yeah. That's why you see transpose over
Yeah,
here.
transpose.
It's a vector. So, that's the way it works here. Because if you look at it, beta 1, what is beta 1 for this typical example? Is a weight on this net, this one, and so on and so forth. All the connection to the first node in the first hidden layer. So it's a vector.
But my question is, if it is one number, at last, fx is one number. But if you want to classification, like you have 1,000, I mean,
Oh, you're talking about this side.
Yeah, how do you
Yeah.
You just compensated with the number of Ks, I guess. For a problem that is like has a very high capacity, you just have to increase the Ks.
even number of
Not
Ks,
a
because
tall
they
number,
added
wide
the weighted sum them together is one number. So fx like this one number, right? Just one scalar value.
Okay.
But how do you do a 1,000?
So his
categorical-
question-
there's a 1,000 image category there. How do you categorize that?
Yeah.
You want to generalize the classification.
Yeah, he wants to
How
he wants
do
to
you do
say, for example, for like a given image, you are expecting like if you put it in 0 and 1, 1, 1, 1. For example, 0, 0, 0, 1, 0, 0, 0, right? You have, let's say, in the last layer, you have more than one node. But here, we have just one node. I think his question is, usually in the classification questions problem, we have more than one node in the last.
Yeah, but how do you do
Yeah,
that?
so that's a valid question, absolutely. So if you refer to this theorem, it says from multivariate input to the real number. It doesn't tell you fx is a multivariate
I was
high
thinking-
dimensional.
Yeah, I was thinking the beta is a
wait,
matrix, not just
Sorry?
a vector.
Beta is a matrix.
Yeah, I think it's matrix. So you
Yeah,
when you
beta-
come out,
no, beta-
it's a
beta-
vector. It's not just a singular value. Right?
No, beta is a vector. Beta is a vector, but when you multiply by x, is a number.
X is also a vector.
Is it x
Yeah,
is
I
also
thought beta is a matrix, it's X vector. Then when it come out, it should be the vector.
No, it's
No,
a number.
beta is a
No, it's a
vector,
number.
so-
So beta times this is a number. When you apply h on top of it, it still is a number. When you multiply by beta, gamma k is still a number, and then you aggregate a bunch of numbers, it gives you a number. But if your question is what we can say about multi-dimensional
Yeah.
cases,
How do you do that?
how that works, at least from the theory here is not clear, because I mean one case, because the main theorem that it says these are dense, these type of functions are dense in the multivariate function. That's for univariate in terms of like one dimension. I haven't seen the multivariate case, multi-dimensional case, but maybe you can add, you can say, okay, I don't care about the theory behind it. How about if I add different layers, different nodes here, exactly the same. I keep the architecture like this, and then I make it fully connected.
Are they using backpropagation for this?
They claim, yeah.
So maybe if you have, this is one output, but if you have one and another output, you just
So
have a
that
different
would
set
be
of
that would be
comments.
exactly what he's saying, right? Because if you go back to your equation,
Yes.
if you replace betas with matrices that are number of outputs times number of inputs, essentially, right?
Yeah, basically,
Then you get
vector makes
vectors.
sense.
So
The
it's
thing
all
is, like,
good.
it could be just
This is exactly
just
what
have-
you were saying.
Yeah, different set of gammas for the second output.
It's just a vector. Most of your work is high dimension, not just one dimension.
Yeah, absolutely.
So if
Most
I
of-
have just one dimension, what you mostly is useless.
Yeah.
No, in some cases you can use it, especially in finance, in some rare cases. But as you said, absolutely, it's a valid question and a comment. In most of the cases, you have more than one node, right?
But I like your idea of adding more nodes at the end.
Well, you can add more node here
Yeah.
and connect it, but there is no guarantee.
I think
That you
you
can-
need, I think you need to repeat the same network for each dimension.
Which is practically equivalent to what he's saying.
Say,
Yeah,
It's just like,
different.
You know, just turn those into matrices instead of vectors. Like
Oh.
betas, if betas are
Yeah.
matrices,
It's
then it's all good. Like,
Because if the age is a full connect network,
Yeah.
if the input just one number,
Yeah,
and now
you're right.
see a full connect
That's
neural network have one
that way.
input.
No, you're right.
That doesn't make sense.
there are different ways that you can extend this approach, but when it comes, at least for this architecture, they are saying that is backed by theory. That it's, in theory, there is a guarantee that you can get exactly the same answer, like a good approximation here. But when it comes to multidimensional, your approach, you can try it exactly. In the last layer, you can add nodes, and then you come up with the architecture, again, new architecture. So, yeah.
I think the theorems for multi-dimensions is just just repeating the whole thing. Like different betas and different, not only the last layer.
Yeah.
Different betas.
Different beta as
different
an
for
input.
each, so per dimension.
So you
Per
can claim that you can build this architecture, but when it comes to, I'm just trying to make a connection with the theory behind it.
I can help it. I
You
think
can.
it's,
Okay, perfect. Yeah.
No, per dimension you can approximate. Per dimension. you
Yeah,
can
yeah, yeah,
approximate.
yeah.
And then
Yeah, but-
it's still universal.
But when it comes
It's
to
dense. I mean, dense.
dense in high dimensional.
Yeah, because
Yeah.
per dimension you're approximating correctly. So it's,
Okay. Okay. So I think we have time. Like,
Sure, keep going.
Yeah. Okay. Perfect. I think it's engaging conversation. So I'm trying. So we already addressed this part. So just some notation. We already know that the projection layer used linear activation function. We said that why we have to use it. Also in the final layer, the weights here connecting the first layer to the second layer, they are like the betas in the inside the parentheses. You might ask, so what is going on inside each box? What is the activation function for each hidden layer? That's also, this kind of, you have to predetermine like functions or parameters, hyperparameters you can use. So in the paper, they're trying to provide 3 examples and see the impact to see how this architecture works. In the first example, they use the first 3 Legendre polynomial. You can see the equation number 3, f1, f2, f3. So the whole idea is they're going with these 3 polynomials. They are not their goal is not to replicate, to exactly come up with the same shape as. For a second, let me show you on the left-hand side. On the left-hand side in this slide, f1, f2, and f3 are presented linear, cubic, and quadratic functions. So they are not going to exactly replicate the network replicate these shapes, but they are hoping that the architecture of X and N tells you, for example, if they apply f1 on x1, so you simulate 5 variables, x1 or x5 from uniform distribution -1 and 1. Let's say you simulate 50K. And you just use 3 of them, x1, x2, x3. And then you apply f1 on x1, f2 on x2, f3 on x3. So there is the impact or the contribution of x1 or x2 in f3, right?
Yeah.
It's just x3. So they are hoping that the architecture tells you that the architecture can capture somehow the impact of a function which is an approximation of f3 and tells you that f3 is a significant variable for that function, not x1, not x2. So this is the architecture. We're going over this again. But the architecture they're using, they simulate x1 all the way to x5. They use x4 and x5 just for noise. They just want to see if architecture wrongly capture x4 and x5 or no, because we don't use x4 and x5. And so the first layer, the input layer, they use 5 variables, 5 features basically. And each subnetworks, they use 2 hidden layers, and the structure of each of these subnetworks is 2 hidden layers, 25 and 10, and then they give it a second try with 12 and 6 hidden node for each hidden layer for each subnetwork. They use activation function. They propose all the well-known activation function, but here they use tangent hyperbolic. And then for the parameters, because we have so here, if you look at it, on the right-hand side is a result of the architecture. So first of all, here they use 5H. They use 5H, meaning that they have 5 subnetworks. And on the right-hand side, the second column, it tells you. So if you look at it at the left column, the first column on the right-hand side figure, you can see the first subnetwork. This is the output of the first network. It gives you somehow a linear function. Second one gives you quadratic. Third one is somehow looks like the cubic one. And what is on the second column on the right-hand side is the first one is, it says for the first subnetwork, H1, X1 is significant. For the second one, X2 is significant. For the third one, X3 is significant. But if you look at here, F3 of X3, look at the coefficient of X3, for example. is going, we have 5 over 2, and then we have minus 3 over 2. One applied to the x and another one to x cubed. But it doesn't tell you the networks, this shape. It just tells you that here, the function that is trying to somehow approximate or mimic f3 has just single significant variable, which is x3. And the rest of the networks, it says the contribution is 0. So they're not significant. And just the first, just 3 of networks, subnetworks, then capture that summation, which is in equation 4. When you simulate 5 variables, 3 of them apply the first 3 Legendre polynomial and then aggregate. So you simulate your data and then you come up with let's say 50k of inputs, x1 all the way to x5, and 50k of outputs. And then you feed it, train it, your XNN, and this is the results. A question?
Yeah, what's the x1, x2? Is it 5-dimensional data, right?
Yeah,
yeah,
exactly.
Okay, so go back to one. Yeah, so like f1, f2, like the h1, h2 in the former slide, right?
Well, it's difficult to say that, but apparently in this simple example, it tried to say, because you can, because if you know, here you have f3 is 1 over 2, like this form, right? But in the if you look at h1, h2, h3, they apply on beta, which is a vector of beta 1, 1, beta 1, let's say, is a vector of in 5 dimensions times x, and then apply another function f on top of it.
Yeah.
This network, this architecture, somehow, as they claim in the paper, and it's clear here, they are not trying to mimic exactly H3, or right, F3 here in the previous case. They have a concept called recoverability of the underlying generating process, data process. What does it mean? To me, it means that they don't need necessarily to come up with an exactly close form of this. But here, apparently, it looks like it's similar.
No, I mean, this is an example of the formal structure they
Yes.
present, right? So
Yeah.
there should be and at least some part of that should be H1, H2, H3.
Yeah, okay.
So, but go back to the
Yeah.
Yeah. So, like F1, why does F1 only have a X1 as input? What's the other 5? The other 4? X2, X3, S4, S5.
They don't use it. They don't apply it. They just want to see if the networks somehow can approximate F1 and tells you if only X1 is important for this
Yeah,
function.
it only have F1. Of course, F1 is important.
No,
Because
yeah,
the other 4 is not there.
They are not there, yes.
So it's not important. Of course, it's not important.
No, but the model doesn't know this. The model, our goal is that the architecture capture that part. The XNN, we hope that XNN, when you apply on this data, tells you that for one of the function, X1 is important, X2 is not, X3 is not, X4 is not, X5 is not.
You didn't put the other 4x there.
Yeah.
How could you know the other 4 is important or not? You only put x1 there.
Yeah, because we apply F1 on X1, and then we aggregate with F2 and F3. We already know that is our generating process. We know, and then we are going to test the architecture. If the architecture tells me that X3 is the only important variable for F3.
The result of the Y is basically the plane in the 3-dimensional space. I don't know, go back to the previous slide.
Here?
Yeah, so we have the Y is equal to F1 x1 plus F2 x2 plus F3 x3.
Yes.
Yeah. So the Y is the plane in the 3-dimensional space, am I right?
Sure. It's 5 dimension.
What's that?
It's at 5 dimension. It says
Yeah.
S4 and S5.
X4 and
Yeah,
S5,
they've got like
Yeah.
constants in the last two.
Yeah.
Because in the next slide, I cannot see that plane. And then your question coming to my mind that, okay, if I have more f or more h or more number of things,
Yeah.
then most probably I end up with a much more accurate approximation of that plane. Can you say that?
Yeah, I think what they're doing, if you go back,
Yes.
what they're doing here is that they're grabbing the three of, the Legendre polynomial
Polynomial,
functions,
yeah.
right?
Yes.
And then add them up, and then with like on different dimensions, as you say, on 5 different dimensions, and that's it. Then they forget about how they built it, right?
Yes.
So
Yeah,
then
they
they
think
grab, right?
They just
then-
aggregate it
Then they grab the resulting function
and feed it.
and see if the network can replicate it. And then what they get on the previous slide is the result of that. So this is like each of these 5 are different H's that came out of the
Out of the
replication.
network.
So there is no one-to-one relationship between F's, F1, F2, F3, and these. Just the network has learned
Yeah.
that these are the F's.
Yeah, these are interesting shapes.
Kind of.
Exactly.
Yeah, they have a term of recoverability.
Yeah.
Absolutely. They are trying to mimic somehow to get the shape of it.
Yeah.
But you see here it says x. If you look at the magnitude of x3 for this one, from here, you might guess, okay, that somehow tells me about f3. But f3, it has its own coefficients, and
You're not telling anything to the network about the fact that it is F1 plus F2 plus
No.
F3. You're just showing it Y, which is the result
Yeah.
of that
Yeah.
aggregation.
But my point is that at the end,
Mhm.
the system, we are not seeing that how accurate the system is.
Sure.
No, it's just overall behavior.
Yeah.
of
So
what
if,
it
if,
is at,
if,
yeah.
if I can see the accuracy, then maybe I can see that, okay, the other 2 dimensions, those are not exactly the one line or one space there.
Yeah.
There's a shape there too as well.
Yeah.
That's what I'm thinking.
So back to your point here, yes. The way that they presented this example, it was just to say, for example,
It's possible.
it's possible.
Okay.
But I think the main maybe motivation for the authors is how. So maybe you can ask, what if my data generating process is nonlinear? Then it has nothing to do. In advance we don't know what is F1, what is H1, what is H2. In this case, it happens that we have F1, F2, F3, we aggregate, and then you might guess, okay, so it has a linear combination of nonlinear function, for example. So each of these graphs should give me the shape of that function. But how about this case? We have a data generating process. We have 2 variables, x1 and x2. We multiply, we use exponential e to the power x1 times sine of x2 plus an error term. So here we have 2 variables, x1 and x2. We simulate it from a uniform distribution on -1 and 1, and then we simulate y 50k. Again, we try to train the network. So here we don't have f1 plus f2 or f3. Is completely nonlinear, is nonlinear function of x1 and x2. But we know if we train an XNN network like model, for sure we are going to come up with h1, maybe h2 and h3. So meaning that we can approximate y, which has this nonlinear form, based on the summation of those rich function, those function h1, h2, all the way hk they call rich functions.
But here the function is not deterministic when you have this randomness.
Yeah.
What are you approximating? So will you recover the exponential times the sine?
So they are trying to somehow approximate in the sense that the out of sample performance of the test. They are trying. Here we have an error here, which the variance is is low. They are trying to add it. So for a second, forget about like the error. Then you are going to come up with a nonlinear form of y. They train, and then you are hoping to come up with f1, h1, h2, or all the way hk. here they add a noise on top of it. To me, it seems like they are insisting on this point that we are not trying to exactly capture, because I mean here we have a nonlinear nature of the model of the data generating process. We are trying to use another surrogate model to explain. That's why the whole interpretation, explanation of these like model comes into play. Like they are trying to see why x1, what's the contribution of x1, what's the contribution of x2 on this data generating process. They feed the model again with the same architecture as the previous one, but here is a bit like the difference is, I think if I remember correctly, so they use 10 edge, like mean 10 subnetworks, and they try to train that networks to using the four variable x1, x2, x3, x4. Again, uniform distribution. They use they don't use x3 and x4. They just use x1 and x2 in this form, and yeah, you see here 10 subnetworks. They use 12 and 6 for the architecture, and they use L1 penalty to control like the overfitting and the parameters. So this is the result of the network. On the left hand side, you see that so out of 10 subnetworks, 2 of them have this form. The rest are 0. So you see like the first, for example, subnetwork and the second subnetwork. This is the shape of it. And for this first subnetwork, it tells you x1 and x2 are significant. The second network also tells you x1 and x2 are significant, but with a different sign. And so as you see in the third bullet, so x and n approximate the simulated nonlinear function with here based on the architecture of the network, just f2 and f5 have this form, the rest are 0. So they are trying to come up with f2, and if you look at it, this is a kind of the beta, one of the component of the vector beta 2, because it's related to f2. The coefficient of x1 and the coefficient of x2. x3 and x4, they don't have. The coefficient is 0.
So does that also imply that they pick a k equals to 10 that might be too big for this answer?
Yeah. Yeah.
Okay.
Exactly. You might say, okay, why 10? How about if I use 4? If I use 20? They don't discuss this. They just discuss briefly in the paper about like practical aspect of the model, of the architecture. Again, all those, you know, art kind of, you know, you have to come up, maybe you can use cross-validation approaches, other approaches to play around with the model to see which combination works better. Yeah.
I'm a little confused by the
Yes.
functions.
Yeah.
Do you not expect to get a periodic function since you have a sign in your original function?
But you only query points from -1 to 1 in X.
Yeah.
So you don't see the
Because the domain, the domain is limited to -1 and 1.
Cheating.
Yeah.
I mean, hold on.
Yes, yeah, go ahead.
Both sine and exponential are like fairly linear in that space, right?
Sort of.
Mostly.
Sort of, yeah.
But can you tell me, for example, what's the shape, the F2, the second subnetworks? Does this shape tells you something about like another closed form of a something, of a function?
I mean, if I want to think about sine between -1 and 1, like the top looks like that, the bottom looks like that, right?
Like this or like this?
I mean, like imagine sine between
Minus
-1
one.
and 1, right? It is like that, right?
Yes.
So if you
It could be the
put
power.
these together, essentially, yeah, it is.
Somehow might tell you something, right? Yeah, but so that's you somehow you're good at this, and you said, okay, I already had e to the power x1 and sine. When you multiply both together, then you are expecting maybe something like this. But to me, still, this is not clear. Is there any close form for this? Each of these subnetworks shape?
Sure.
You might fit n different functions on this interval. Like so, yeah.
So as you have more data, your network, you expect your network architecture to change, right? To have k-may increase with more data. In comparison to for example, CNNs, where you have a fixed architecture. Even if the data changes, you still have the same architecture. You can use it. For example, use the first few layers, fix them, and just change the last.
So your point is,
I mean, this network changes according to the data.
no.
To the amount of data?
No.
And if you have a new data,
It's like a fit for-
that didn't see it.
Is it not like every fit for all, like fully connected, any other like other architectures? Like if you have a new data, for example, you cannot say globally. What you can say globally, if you already fit your data, your architecture, you came up with a perfect architecture for a given problem, then yes, you say, okay, my architecture is fixed. But if you don't know, and the problem is locally somehow for a given problem, new problem, which is different from the previous one, then you need to play around with the architecture, no?
But I still don't understand your point. Increasing the amount of data shouldn't change the architecture. What do you think it would?
Maybe.
You mean a different case that's been
Maybe it didn't cover the whole data, but I think,
So you're expecting the more data we have, the level of complexity of the architecture should rise, right? Or getting more layers or more?
Like what if the data changes
Why?
from, I don't know, -1 to +1 from, I don't know, 10 to 20, right? So how would that change? Different types of data.
Like increasing the dimensional? Like are you changing your assumptions about your input data?
Input data, yes.
Okay, sure. If you change
I
your
think that's what
assumptions,
it
you
is.
have to change your model.
Yeah.
That's what
But
it is.
increasing the amount of data shouldn't, because
But,
if
yeah.
the assumptions are still the same.
Yeah.
It doesn't. I think it doesn't matter if you simulate 50K or, well, maybe in terms of tuning a bit, in terms of like making the performance better, change a bit. But if you simulate 50 versus 60K, do you think like is a big changes we have to do on the network?
Didn't try this on, for example, images?
No. This is this has been published, like put in an archive last month, and still you don't see application in finance. It's purely yeah.
What are we waiting for?
Exactly. It's just that's why at the beginning when Amir asked me like we have a networks, underlying network. What's the connection between that and the subnetworks here? In this paper, they don't talk about the given network. The only thing that they do, they come up with this architecture, they introduce it, and they apply it on 3 different functions. One of them was the aggregation of Legendre. Second one is somehow similar to that. The third one that I picked it here is nonlinear. And then they just want to see if they simulate data based on this data generating process, how the architecture behaves. No application in finance, nothing, or other industry. So I think, yeah, I think it was interesting, like engaging this conversation. If you don't have question, I can switch to here, the last slide that I'm trying to. When you read the paper, what they claim and what it comes into your mind, for the sake of interpretation, explainability of the the neural networks, does this model, this architecture, address what they claim to some degree or no? So the first one, I think before going to each of these questions, the interesting part here, I think, is from this, from the explainability of model, which variable globally is important for your model. Because here, inside each of these hk, you have beta x. So from the coefficients of beta, the beta coefficients, you can say something about which variable is significant. I think that was the main, or maybe contribution, or that's the part that I liked from this architecture, rather than when you compare it with this part, on the left-hand side. It doesn't tell you. There are some approaches you can use by aggregating weights across all layers and nodes, and say, okay, when I aggregate all weights, then I can say which variable is important, variable importance techniques for fully connecting neural networks. But in this architecture, at least based on this single to single, like input and output, it can tell you like what is the contribution of each of the elements of the vector x in this architecture. Or as a whole, that's their goal. Hopefully, that's why here I emphasize, they just want to say x3 is important in this architecture. They don't care about what's going on inside that. Or here, we know that x1, we already know that x1 and x2 are important, and that the network tells you x1 and x2 are important.
Is there a guarantee on sparsity? Like, for example, in your examples,
yes.
What if the coefficients for x1 to x4 were kind of all large, you know? So like that approach makes sense because, like in examples that you showed, because there seems to be a bit of sparsity
here,
which is by design,
for example,
right? Because if x1 to x4 is important for all the terms that you find, then what can you really tell about the interpretation of your results?
Yes, that's a very good question. This is in line with the last slide that I am somehow criticizing this approach in this, because the way that they're trying to sell the paper is it addresses the interpretability problem. Mm-hmm. But to some degree it addresses, as you mentioned, if the coefficient of x1 all the way to x4 are non-zero, then you can say, okay, these variables, they have contribution, but what else? Like, if you want to perform some kind of sensitivity analysis, just the partial derivatives, for example, mm-hmm. what you can say? Do you have the closed form of those h? Because h are important in the, yeah.
Maybe I would think about this in terms of making it usable. If you're doing your credit score example,
yes,
and you have this XMN that shows you that different factors have certain behavior, what you would do is you would vary them all, and then you would look at the changes in each of the graphs, and you would see if it gets steeper. And then you would go, you know what, the contribution of the second coefficient, whatever it is, when it increases, your thing gets steeper. So therefore, maybe there's some aspect of that factor in your credit score that gets worse faster. Mm-hmm. And therefore, if you get worse, if you take on too much credit, it looks like your credit score is going to go down much faster.
So you're talking about like if we give it a try and doing like numerical, like shock it, like play around.
Yeah, exactly.
Then you look at the direction of where the credit score goes, and then we might say, okay, this factor,
especially like that variable with respect to the credit score
itself.
itself, and you look at the behavior, or at least you intuit the difference in the shape of the graph.
Yeah, that's doable numerically. Yeah, that's correct. But I think it's difficult from this exercise to conclude something globally, right?
Yeah, you would get the impact of a certain variable for sure, or you would think you do.
But if you imagine, if you look at it like as a regression model, mm-hmm. that beta x, that beta tells you a lot. Mm. But so
So is this like the behavior of the beta for a given coefficient?
Well, here we have one beta inside the parentheses, but at the same time we have that h, which we don't know what is h. I think that's also play a big role in understanding the concept of like interpretability of the underlying model. This paper, they're addressing the connection between input and output, and they claim it. They say, okay, in highly regulated industries, including banking, they are interested. They want to see the full connection between input and output, because when they're doing like kind of stress testing exercises set by regulators, then they have to use macroeconomic variables, and that the impact of those variables are so important for the sake of like forecasting or projecting the risk parameters, for example. So those betas, yeah, it tells you the contribution of x1 in the first function is this one. But to me, this is not enough. This address just the connection between input and output, but that h also is important.
It is that they cannot quantify the effect globally.
Exactly.
Because for example, f1x equal x1, f2x equal minus x1. So basically, you can see different beta will be very big, but actually these two will just equal out.
Cancel out.
Yeah.
Yeah. Yeah. Exactly. So the shape of function is also important, right? So not just the shape, the form of it. So if I wrap up like.
Sorry, can I ask another question?
Yeah, sure.
Can you go back to your this one? What is the horizontal axis on the images?
On the images.
On the middle one, sorry. On the
this one.
Yeah.
So this is a domain of your variable, like -1, 1.
Is it for
Sine? But they adjust it because you don't see here the gamma, because we have gamma as well, the coefficient of. So they adjust it. So.
Yeah.
So if you go over these questions, natural questions comes into your minds, my mind. So is XNN is a class of, with a built-in interpretation mechanism? We discuss it. Yeah, to some degree, yes, but it's not fully. Can we approximate or try to understand the primary model based on XNN? Because this architecture is based on theory. In theory, you can approximate very well any multivariate function. But when it comes to practice, because of those hyperparameters you have, tuning, and because of the architectures of those subnetworks, it's difficult to say, at least to me, it's not clear. And then in the paper, they provided 3 examples. The complicated one is e to the power x1 sine x2.
That's not very complicated, right?
In this paper. In this set, yeah. So can we generalize the performance? Because they say, okay, the out-of-sample performance of the model for this data generating process is very good. But what we can say, in terms of performance, out-of-sample performance of the model architecture as a whole. We don't care about like in-sample. Okay, fitting the model is fine, but how about, because we are going to use this as an approximator for the primary model. So we can maybe we can fit this curve with several functions. Okay, up to this interval performs perfectly and match perfectly. But how about the new simulation? So another question: does XNN say anything about the closed form? No. Again, sensitivity analysis, that's a contribution of the rich function, those h and the feature to the feature, or contribution of h to the whole output of the model. And again, what's the impact of different nonlinear activation function and other parameters on the final model performance. So